and welcome to another video. On the board are two questions on electrostatics, that is the study of electric charges at rest, or the study of static or stationary charges, or the study of static electricity. Alright, so the first task is to calculate the force between 2 point charges, positive 1.4 nanocoulomb and positive 1.6 nanocoulomb, on point conductors 40 centimeter apart in air. Then the second question, what size of charge on a third point conductor placed midway between the first two conductors would result in doubling of the magnitude of the force on the 1.4 nanocoulomb charge? So we are given the permittivity for air to be equals to 8.9 times 10 to the power of minus 12 farad per meters. So for the first question, that's A, our task is to calculate the magnitude of the force between two positive point charges of magnitude 1.4 nanocoulombs and 1.6 nanocoulombs, okay, on the conductors, okay, separated at a distance of 40 centimeters apart. So that means we have two conductors. The first conductor, okay, carries a charge of magnitude 1.4 nanocoulombs. So let's say this is the first conductor is denoted with, that's the first conductor carries a charge of positive Q1. Then the second conductor carries a charge of positive Q2, and the magnitude is the positive 1.6 nanocoulombs. So these two charges are separated at a distance r apart. That is, the distance of separation will be 40 centimeters. Okay, so which means according to the question, we are given the magnitude of the first positive test charge or point charge to be positive 1.4 nanocoulombs, okay, and then the magnitude of the second positive charge, okay, is positive 1.6 nanocoulombs. Now let's not forget that 1 nano, okay, is equals to 1 multiplied by 10 to the power of minus 9. So which means 1 nanocoulombs will be 1 times 10 to the power of minus 9 coulombs. So these two charges, okay, two charges of magnitude 1.4 nanocoulombs and 1.6 nanocoulombs are separated at a distance of 40 centimeters apart, okay, in an homogeneous and isotropic medium. That's why we have permittivity for air to be equals to 8.9 times 10 to the power of minus 12 farad per meters. Now, to calculate the magnitude of the force between the two positive point charges, okay, so let's say an electric force Fe, okay, act on charge Q1 due to Q2. The magnitude of this force will be proportional to the product of the magnitude of the two positive point charges and inversely proportional to the square of their distance of separation, okay. That means according to Coulomb's law, you know, Coulomb's law states that the electrostatic force of attraction or repulsion between 2 point charges, just like we have here, we have two positive point charges. So we have the first charge to be labeled with Q1. This is the conductor. The conductor carries a charge of magnitude 1.4 nanocoulombs. Now the second conductor carries a charge of magnitude 1.6 nanocoulombs. The two conductors carrying these two positive point charges are separated at a distance 40 centimeters apart. Okay, so when an electric force acts on any of the two charges, okay, due to the other, okay, the electric force will be proportional to the product of the magnitude of the two charges and inversely proportional to the square of their distance of separation, and that's the statement according to Coulomb's law. Okay, so we want to calculate the magnitude of this force. So we have that from Coulomb's law. I want to believe this is correct, the spelling. From Coulomb's law, we have that the force, that is the electric force, is proportional to the product of Q1 and Q2, okay? And at the same time, inversely proportional to the square of the distance of separation between the two charges. All right, so now, so in this case, when this is changed to, whenever this is changed to equality sign, then we're going to introduce a constant, okay? We're going to introduce a letter, that's letter K, and that K represents the electrostatic force, that electrostatic constant, okay? So in this case, we're going to have the electric force to be equals to K Q1 Q2 over R squared. Now, the value of K will be 9.0 times 10 to the power of 9 Newton meter squared per coulomb square. That is because if you replace K, K can be replaced by factor 1 over 4 pi epsilon. And we're giving the epsilon to be 8.9 times 10 to the power of minus 12 farad per meters. So when we plug in this, the value for E, okay, we will plug in the value for E. In this case, we're going to have this formula will then be Fe equals to 9.0 times 10 to the power of 9 multiplied by Q1, Q2 divided by R squared. So let's not forget that we're given the distance. Distance is 40 centimeters. And 40 centimeters will be 0.4 meters. Okay? All right, so for question 1, the magnitude of the electric force will now be 9.0, okay, times 10 to the power of 9 multiplied by the magnitude of the charge on the first conductor, which is positive 1.4 nanocoulombs. And that will be 1.4. This will be 1.4 times 10 to the power of minus 9, then multiply by Q2, which is positive 1.6 nanocoulombs. And this would be 1.6 times 10 to the power of minus 9, all over 0.4 raised to the power of 2. Raised to the power of 2. Okay, so what is 1.4 multiplied by 1.6? That is 1.4 multiplied by 1.6, then multiply by 9. That will be 20.16. So that the electric force will be equals to 20.16 times 10 raised to the power of 9 multiplied by 10 raised to the power of minus 9, this guy, multiplied by 10 raised to the power of minus 9, this second guy, all over. So this is same thing as 4 times 10 to the power of minus 1, that is 0.4. Then when raised to the power of 2, it will be, okay, let me write this, 4 times 10 raised to the power of minus 1, then raised to the power of 2. So that the electric force will be 20.16 times 10 raised to the, if you're applying this is here, okay, that is write one of the base 10, and then add the exponent. Then we're going to have my 10 raised to the power of minus 9. So this will be divided by 16 multiplied by 10 raised to the power of minus 2. So I'm going to divide 20.16 by 16, and that will be 1.26. So that the electric force will be equals to 1.26 times 10 to the power of minus 9, then divide by 10 raised to the power of minus 2, that will be plus 2. Let's not forget that the unit of force is the Newton, so we have this guy to be equals to 1.26 times 10 to the power of minus 7 Newton. So this is the electric force, okay, the force of repulsion, because in this case the force will be a repulsive force because the two charges carries the same, the two charges are like charges. And you know, another statement credited to Coulomb's is that like charges of electrification will repel each other, while unlike charges of electrification will attract each other. Okay, so which means this force will be a repulsive force because we have like charges. This is positive, positive, or we can say similar charges. So similar charges will attract, will repel each other, while unlike charges will what? Will attract each other. Okay, so B, what size of charge on a third point conductor placed midway between these two charges, okay, between the first two conductors, okay, would result in doubling of the magnitude of the force on the positive 1.4 coulomb charge. So which means what this what we are asked to do here is that now we have the first two conductors. Now the first conductor which has a charge, that is with carrying a charge of magnitude positive 1.4 nanocoulombs, and the second conductor, which is what we have, carrying a charge of positive Q2 of magnitude positive 1.6 nanocoulombs. Okay, and we know they are separated at a distance of, the distance of separation is 0.4 meters. That's the distance of separation. So now, what size of charge on a third point conductor? That means if you have a third conductor midway, placed midway, what size of charge? What is the charge on a third point conductor that is positive Q3? Okay, what is the magnitude of this charge? Okay, placed midway between the first two charges, between the first two conductors, okay, would result in doubling of the magnitude of the force on the positive 1.4 nanocoulombs. Now, this is it. The force, now, in this case, this will be 0.2 meters, and this also will be 0.2 meters. That's midway. All right. So, which means that the force on Q1 due to Q3, according to that, I want to answer the question, using a verbal statement now. The force on Q1 due to Q3, okay, would be equals to, that is for the force to be doubled, then it will be equals to the magnitude of the force on the two conductors, on the magnitude of the force on the two charges Q1 and Q2, which is this value we got here, okay. The force will double, okay, when the force on Q1, that's charge Q1, due to Q3, that is F13, okay, is equal to the magnitude, of the force on the first two charges on the two conductors. So that means I'm talking about F of F12. This one is F13. So which means that this simply means that F13 will be equals to F subscript 12. Okay, so which means the force will double. That is, what size of charge on a third point conductor placed midway between the first two conductors. So we want to know the size of the magnitude of this charge, okay, would result in doubling of the magnitude of the force on the positive 1.4 nanocoulomb charge. So what that means is that the electrostatic force of repulsion between charge Q1 and Q2, which is F13, So we have F13 to be equals to F12. What is F12? F12 is equals to 1.26 multiplied by 10 raised to the power of -7 Newton. So this value 1.26 multiplied by 10 raised to the power of minus 7 will be equals to, now let's not forget that the force is equals to this, okay? It will be equals to 9.0 times 10 raised to the power of minus 6, then multiply by Q1, Q3 over 0.2, then raised to the power of 2, because the third point conductor, okay, is placed midway between the first two conductors, okay? So midway, that is half of 0.4 meters. Okay, so now we already know that the value of Q1 is the positive 1.4 nanocoulombs. So I'm going to plug in the value. So we are looking for Q3. So to calculate Q3, so I'm going to make Q3 the subject of the formula. So I'll multiply this 1.26 multiplied by 10 raised to the power of minus 7. Then multiply by 0.2 raised to the power of 2. That will be 4 multiplied by 10 raised to the power of minus 2. So this will be 4 multiplied by 10 raised to the power of minus 2. Then I'll divide it by 9.0 times 10 raised to the power of minus 10 raised to the power of 9. This will be 9. Okay, let's not forget that we're using 9.0 times 10 raised to the power of 9, which is the value of K. That is the electrostatic constant. Okay, all right, so then multiply by Q1, which will be 1.4 times 10 raised to the power of minus 9, because we are given positive 1.4 nanocoulombs. Okay, so again, let me multiply 1.26 multiplied by 4. That'll be 5 points. So we have Q3 to be 5.04 multiplied by, so I will combine this, minus 10 raised to the power of minus 7 multiplied by 10 raised to the power of minus 2. Then 1.4 multiplied by 9. This is 12.6. Then times 10 raised to the power of 9 multiplied by 10 raised to the power of minus 9. So if you apply indices here, one of the properties of exponent, this will be 10 raised to the power of 0. So what is 5.04 divided by 12.6? That will be 0 points. So we have Q3 to be equals to 0.4, then times, this will be 10 raised to the power of minus 7 minus 2. Okay, and this Q3 will be equals to 0.4 times 10 raised to the power of minus 9. Now the unit of electric charge is the coulombs. So it means that Q3 will be equals to 0.4 nanocoulombs. So this is the magnitude of charge on a third point conductor placed midway between the first two conductors, which will result in doubling of the magnitude of the force on the positive 1.4 nanocoulomb charge. The noblest pleasure is the joy of understanding. Bye-bye.